We see now an example of a separable Hilbert space. This is one of the most important Hilbert spaces. However, as we just said, all the Hilbert spaces are the same. However, it's convenient to have a precise representation of the Hilbert space. So this is an example. This example is called little L2 of R, and is defined as all sequences real value, all the sequence with the property that the sum of the square elements is finite. This space has endowed with the scalar product so given two sequences xn and yn, the scalar product is the sum of xn, yn. Right? So as you see, this is just saying that the norm is finite of these elements. Okay. This is a Hilbert space, but this is a particular example of Hilbert spaces that we already observed. So it's a Hilbert space for is the L2 space of some measure space. In fact, observe that on the natural numbers, one may consider what's called the counting measure so is the measure mu, defined as the sum of the masses on singleton, okay, where delta, maybe we should not put the parenthesis, just delta n is the Dirac mass, it's the Dirac mass at n. Okay, that this measure just given a subset of n tells you how many points you have in this set. Okay, so what we have is that this space L2 of R is nothing else than the L2 of the measure space given by n as a set. As sigma algebra, one can take all the parts of n, and the measure is this counting measure. Because exactly, so if you have a function, what is a function valued into R, this on this space, this is exactly a sequence, and having finite L2 integral, this is exactly the integral of the square function. Okay, so since we saw this, we are seeing this, we can see this example as a L2 space, then we have this little L2 is a Hilbert space. Very good. Another Hilbert space that we saw was L2 of the real line with the Borel subset and the Lebesgue measure. So these are two different Hilbert spaces, at least set-wise. Right? So, but as a consequence of the theorem that we proved before, the space little L2 and capital L2 of R Borel sets and Lebesgue measure, these two, and we can also we can also take L2 of 0, 1 with the Borel set of 0, 1, with always the Lebesgue measure. Okay, restricted to 0, 1. Right? All of these are Hilbert spaces. And I'm going to tell you that these are isomorphic as Hilbert spaces. And this is because all of them are infinite dimensional. That's easy to check, but they are separable. Okay, let me at first convince you that little L2 is separable. Okay, so indeed, let me just write that indeed one needs to just check that they are separable and infinite dimensional. In fact, okay, it's very easy to prove that L2 of R is on this space. We have a countable dense set. Actually, I will just give you a Hilbert basis. So on this L2, the sequence of functions characteristic of n, when n is an element in n. So this is, if you want, is the sequence is always 0, except on the nth element that is going to be 1. This is a Hilbert basis. Okay. Let's prove that this is okay. This is definitely countable. Let's check that this is a Hilbert space. Let's do this simple exercise. So if I take the scalar product between characteristic of n and the characteristic of m, see what this is. This is so I can also write characteristic of n as the function or as the sequence that is delta I n as a sequence in I, right? So this is going to be always 0, but when I is in is equal to n, then the value is going to be 1. So what happens now if I sum delta in with delta im, sum over I? Now, if n is equal to m, then this is going to be 1, if n is equal to m, otherwise it's going to be 0. If n is different than m. Okay, so they are orthonormal. Now let's check that it's dense. So now take x, so it's an element in little L2. So the sum of xn squared is going to be finite. Now, for any epsilon greater than 0, we know that if we sum from n greater than some k, so the tail of this series, then this is going to be going to 0 as k goes to 0. So we can take some k such that this sum is less than epsilon. Very good. So now what we have that the element, let's call it x, maybe I'll put an index n, which is the sequence that is sum of xn characteristic of n, so n from 1 to k, right? So this is the sequence that is x1, x2 up to xk, and then it's 0. Okay, so now we have that this xn belongs to the span of the yn. And I claim that this converge to no, that is this epsilon close to the initial x. In fact, like, what is the norm xn minus x? Sorry, we should not call it n. This should be called k. The index here should be k. Okay, k. Ecco. So k, because this norm in L2, so let's square norm in L2, what is this? This is equal to the sequence that is 0 in the first k entries of the sequence, and then in the rest it coincides with x. So the L2 norm is exactly the sum for n greater than k of xn squared, which we said is smaller than epsilon. So we find sequences that converge to an arbitrary element. So we got a Hilbert basis. At this point, we want to ask ourselves the question of which, if our LP spaces are separable. Okay, the answer will depend on P, especially in the sense that for P finite, the LP spaces will be separable. For P infinite, it will not. Okay. Let's consider first the case where P is different than infinity. So for P greater or equal than 1, P different than plus infinity, and LP of, so let's call it LP, but it's LP of R with the Borel sigma algebra and the Lebesgue measure is separable. Actually, this result extends to every subset of actually Rn with the n-dimensional Lebesgue measure. But let's only prove it for dimension 1. The proof is actually the same. So proof. So first I want you to remember that, so maybe just to understand the proof, recall that the step functions, in the sense of sum of characteristic functions of sets with finite measure, and when in the sum we take arbitrary real numbers, this class of functions is dense in LP. Right, so we already discussed this, and so therefore what we have to do, we have to approximate with a countable set these step functions. And what we will see, we shall see that the set of characteristic functions, but just of intervals a, b, with coefficients, and now what we are assuming is that a and b are rational and c is also rational. Okay, so this class of sets is countable and dense. Countable and dense in LP. Okay, the discountable is clear because it's given by 3 rational parameters. Let's prove that it's dense. And because of what we said, that every set is every function in LP is approximate with a step function, it's enough to approximate the characteristic of a set of finite measure. So it's enough to approximate the function characteristic of a set for an arbitrary A Borel set with Lebesgue measure. So let's write lambda for Lebesgue finite. Lambda is Lebesgue. Okay, so let's use the fact that lambda is a regular measure. Actually, it's up. Most important is upper regular. So the set A can be approximate with open sets, sequence of open sets, such that so what we are going to have that A is inside UN, and the measure of UN minus A goes to 0 as n goes to infinity. So this is about sets. And now what we do, we claim that the characteristic of functions of these sets converge to the characteristic function of A in LP. Let's do it. Let's check. So this is we can just, you have to compute a norm between the two elements. Now this is the P norm. Let's bound the P square of the norm. So this is by definition, this is the integral of R of the characteristic of A x in dx. Okay, now when is it that this is different than 0? It's different. So we have A inside UN. So this is non-zero exactly in UN minus A. So this is equal to the integral over UN minus A of the number 1, which is exactly the measure of UN minus A, which goes to 0. Okay, so therefore we check this convergence. And what is it that we conclude? So we conclude that hence characteristic functions of open sets approximate characteristic functions of arbitrary Borel sets. But now how can we approximate open sets? But then we observe that, recall the fact that every open set in R, each connected component is an interval, and the number of connected components is countable because each connected component contains a rational number. So every open sets are just countable union of intervals. And therefore, again, we can use characteristic of intervals. Now, I should do it in R. Characteristic of intervals to approximate, or some of these characteristics of intervals, to approximate every characteristic of an open set. Now, to use only intervals that are with rational endpoints, it's important that now to conclude, it's again important to observe that if numbers an converge to A and Bn converge to B, then the characteristic of the interval an Bn converges to characteristic of AB in LP. And therefore, the family that we were proposing is dense. This family is dense in LP. Okay, proof is complete. And now let's talk about when the case is P is equal to infinity. When P is equal to infinity, this proof doesn't work because we don't really have this convergence. Likewise, we don't have this convergence here in general. Let's make this as a remark. So remark. So let's give a precise example. For example, for P different than plus infinity, the situation is different. For example, if you consider the characteristic of the interval 0, 1 plus 1 over n, this does not converge to the characteristic of 0, 1 in L infinity. And because let's check what's the distance between the nth element of the sequence and what we expect the limit to be. Now we have to calculate the sup norm, but you see any point that is in between 1 and 1 plus 1 over n will make the first function being 1 and the second one being 0. So this is 1, this is 0. So the sup is at least 1. Okay, exactly as more. It's exactly 1. So this limit doesn't. This sequence does not go to 0. So for sure, this sequence do not converge to this function. And actually, one can use this observation to show that L infinity is not separable. Let's make it as a new page. Proposition. So L infinity of R with the Lebesgue measure is not separable. And the proof is the following. So one can consider the set characteristic of minus infinity A real, and this set is an uncountable. It's an uncountable set that is one disjoint. So points in this set have distance greater than 1. And therefore, the space cannot be separable, because if it were separable, then in every 1/2 ball of this set, you could find an element of a countable dense set, and 1/2 balls would be disjoint. So you have a correspondence between a countable set and an uncountable set. This contradiction tells us that L infinity is not separable. So now let's check that this is one separated. So what I'm saying is that if you take A different than B, then the same calculation of before tells us that there is the difference of these functions has a point with the value 1, and therefore the sup norm is greater than 1, is actually 1. Okay, and as I say, this fact tells us that L infinity cannot have a countable dense set. End of the proof.